Okay. So we are looking at the bond enthalpy question number 17. And when we look at bond energies or bond enthalpies, basically you're saying we are breaking 1, 2, 3, 4 CH bonds. And the question tells us that each CH bond is 414 kilojoules. So we are breaking 4 times 414 kilojoules. Now, when we break, is that endothermic or exothermic? Breaking is endo. And if it's endo, that means this value is going to be positive or negative? Positive. Okay, so this is positive. And so we do that and we get 4 times 414 equals 16, positive 1656. We are also breaking B-R-E-A-K, breaking 4 ClCls, and we are told that ClCl is 200, 4 times 200 kilojoules, so that is positive, because again, we are breaking, so it's endo, so it's positive, so that's positive 800. And then we are forming, so in our products we have, if we go back to our reaction here, we have 4 HCl's and a CCl4. So we are forming 1, 2, 3, 4 HCl bonds. And the value and the energy of the HCl bond is 432. And because we are forming, is this endo or exo? Exo. And so the value of these will be negative. So that's going to be a negative. So 432 times 4 equals, and so that's going to be negative 1728. And finally, we are also forming 1, 2, 3, 4. 4 times, and the CCl bond is 397 kilojoules. So that's going to be negative because it is exo. 4 times 397. Did I get that number right? I feel like I wrote it wrong. Yes, I did. Okay, good. So that's negative 1588 kilojoules. So then we take all of these are kilojoules here, kilojoules, kilojoules, kilojoules. In order for this reaction to happen, we had to put in these guys here, those positive amounts, and we got out these guys here, those negative amounts. And so what we're going to do is we are then going to add them all up. You notice we have our 2 positives here, and we have our 2 negatives here. And if you add those all up, you get 860. Yes?
Wait, I'll make one question. What do you say? What is the difference between the bond energies?
The bond energies and the enthalpy of the equation?
I know, like, it's not, I remember one was like that. It's like the delta H equals like always an R minus reactive.
Yeah, so there are different ways of figuring out enthalpy of reaction. This is one way of figuring out enthalpy of reaction, is to use the bond energies.
So for the bond energy, what's the difference between the bond energies and that?
Enthalpy of formation, it's not to do with a single bond, it's to do with what it takes to form that actual compound from the elements in their natural state. So if you had CO2, you would have bond energies here, yes? I'll get to you in a second, Brian, sorry. So we have bond energies here and here. The delta H of formation for CO2 is not the bond energies. It's if you take carbon, which is graphite, in its standard state, because remember that little H is pronounced not. So delta H naught, and that means at standard state. And you would take oxygen in its most common form, in its standard state, so that would be O2 gas, forming CO2.
So it's like the information is like
yeah, it's just whatever energy, and I don't know how they did it. I presume they went and burned some carbon and with some oxygen.
Oh, it's like the inspiration here, like the product minus reactant.
Yeah, yeah.
For bond energy, you like how much it takes to break
and how much it takes to form. Yeah, so there's two ways. Where's my black pen? There we go. There's more than two. Delta H of the reaction. Okay. Number one, delta H of reaction. Whoops. Let me get rid of that little knot there. I don't think it belongs. It might. I get a little confused sometimes about whether the knots are there or not. I know it's there for the formation. We would have the sum of delta H naught of the products minus the sum of, oh, sorry, I wrote that wrong. Formation of the products minus the delta H naught of formation of the reactants. That formula, number one, is in your data booklet. Okay, so if we go to our data booklet, and I think, is it on page 2? It's on the very back page of your blue sheet, and you can see that we have that one there, and it's products minus reactants. So you don't have to remember that the products come first and then you subtract the reactants. But if you would like to remember it and you want to understand why, we keep the value of delta H naught as is. We don't change its sign because we are actually forming products. Yes? So the products are being formed, so we just keep delta H naught formation as it is. The reactants are being unformed. Therefore, use the opposite of delta H naught F, which means negative delta H naught F. Does that make sense? And by opposite, we mean the opposite sign. Products are formed. So therefore, we use delta H naught as given, not negative. But like I said, if you don't remember that, it's in the formula booklet. Yeah? But it's kind of nice to understand why. Does that help understand why? Okay. Now the second way, and all of these are dependent on Hess's law. You're like, oh, okay, if I take all of my delta H formations and I write the formation reactions and I add them all up, everything will cancel out to give me whatever my reaction was in the first place. Okay. Same thing with the bond enthalpies, bond energies. And this one, I just like to remember that bond breaking is endothermic and bond formation is exothermic. Whoops, bond breaking. Bond forming is exothermic, and therefore those values are going to be negative, and then you just add them all up, okay? I'm gonna call these BE. So you'll take the bond energies and you'll make them positive, and these ones you'll make them negative. There is a formula that you can write for this. You can say delta H of reaction is equal to the bond energy, the sum of bond energies of the reactants minus the sum of the bond energies of the products. Because so it's reversed. So if you're like, and if you understand it, this should help you understand why the reactants need to be positive values when you're talking about bond energy, because you're breaking those bonds. That's endothermic, that's positive. The bond energies of the products have to be negative because they're being formed. That's exothermic. But if you forget that and you're like, I'm on the AP exam and I just don't remember, then you can go to your data booklet and you can say, oh, look, when I'm doing formation, it's products minus reactants. Bond energies are the opposite of that. So you would put the reactants minus the products for the bond energies. Okay, so you can memorize, you can understand, or some combination of both. Yeah? Okay, cool. Any other questions? Brian, you had your hand up at some point. Sorry? Uh-oh. I probably did it wrong. Where did it go? 1656 plus 800 minus 1728 minus 1588 equals, whoa, that was not the value I should have gotten. 165. I taped something wrong. 800 minus 1728 minus 1588 equals, yeah, it should be negative. Negative. And that would be negative. Does the answer key say E? Do you guys remember? I don't know. I'll put a star beside it. Maybe fix. maybe fix. And I definitely have to fix. It says E? Oh, yay! Definitely fix. Okay, so that should be a negative 860. It does?
Yeah.
Oh, no, but I have to fix this in the written, in the explanations.
Oh,
yeah, this part I have to fix. This is fine. Okay, there we go. All right. And just in case you're like, why do we get that? I kind of put this in here because I thought it would be a good chance to review the covalent bond formation energies. Because if you didn't take Enriched last year, you may or may not have seen this graph. This graph, along the x-axis, we have the internuclear distance. What is the internuclear distance? It is the distance between the nuclei. That right there is the internuclear distance. And we're looking at bond formation here. Now, when these two atoms are really far apart, they have no interaction. Okay, so the H and H are sufficiently far apart, they have no interaction, the potential energy is just 0. Okay, because they're not interacting with one another. Now, as they start to get closer, so we're actually traveling this way along the curve, the atoms get closer as we go from left to right on the graph. They begin to attract. And why are they attracting? They're attracting because have a chat with your neighbor. Why are those atoms starting to attract as they get closer?
Yeah, because if it was electron left, it should be all.
Okay, so what's happening that's making these atoms attract?
The nuclear attraction is stronger than the electron.
Yeah, the attraction of the nucleus to the electrons is stronger than the repulsion of the nucleus to the nucleus. So the nucleus electron attraction is what's pulling them together. And right now, the nuclei are not close enough to each other, the positive and the positive, to outweigh that. Okay? Now, at some point, they get close and they start to like almost form a bond, and then we get the observed bond distance in H2. So if you have a graph like this, you can read off the graph, you can say this distance right here that right there is the bond length. Okay? Average bond length. And in this case, 74. I assume that's angstroms. I could be wrong. What does it say? Doesn't say. Oh, picometers, picometers. Picometers, 74 picometers. Do you guys know what a picometer is? 10 to the negative 12, okay? Yeah. All right, so that's our bond length. And you'll notice at that length, what do we notice about on our y-axis, we have our potential energy. What do you notice about the potential energy when we have the average bond length? Potential energy is the lowest.
But what is it negative?
Huh?
What is it negative?
Negative potential energy means it's really stable.
Oh,
Okay, now technically, you can put the 0 for potential energy anywhere you want to. Do you know what I mean? Like I could say the potential energy for this pen is now at 0, right? And I can say I'm setting the desk as 0. Or I can say I'm setting the floor at 0 and this is a positive value.
oh, see, it depends on what you look at.
It depends on what you're looking at. Now, this one is actually set fairly reasonably because it's saying if there is no interaction between the particles, then there is potential energy is 0. So it's not quite arbitrary, right? There's actually a reason for putting it where it is. So if it is negative, you're going to have attraction. If the potential energy is positive, you have overall repulsion. Yeah? Negative potential energy, overall attraction. Positive potential energy, overall repulsion. 0 potential energy means there's no interaction. Would you rather I put this on bigger paper? Because I went half size this time. If we do this again, do you want it in the bigger paper or the smaller paper?
How big would it be?
It would be like twice the size. It would just be like normal size paper. Like the paper would be the same size. It just wouldn't be like half and half. This is fine? Okay. Anyone really want a bigger one? No? Okay. All right. So, yeah. I'm just trying not to kill as many trees, although I'm not really succeeding. I'm killing like all sorts of trees. Oh, it's awful. Anyway, yeah, so we have that, and that is our optimum distance to achieve the overall potential energy of the system. So what you can see then is, if we look on this next diagram, as the bond is forming, that little yellow highlighted part, which is why I did this in color for you, the atoms move from a higher potential energy to a lower potential energy. And as things move from higher potential energy to lower potential energy, is that endothermic or is that exothermic?
So
That is exothermic. So that is why bond formation is exothermic. Yeah? Is that good? I felt like this graph, like how many people remembered this graph from last year? Oh, wow, that's cool. Excited. Was it worth going over again? Yes? Okay. All right, number 21. The standard enthalpy of combustion of CH3OH methanol is negative 709 kilojoules per mole. What is the approximate mass of methanol that must be burned in oxygen to produce 70.9 kilojoules of energy? So we are starting with 70.9 kilojoules of energy, and we want to find the grams And we are told that we have 709 kilojoules per mole. Now, do you guys remember what that mole to the -1 means? It means per. Yeah, it means divide by. So that means -709 kilojoules per mole. So you now have a conversion factor to go between kilojoules and moles. So let's cancel out our kilojoules and find our moles. So that is 709. And I'm not going to worry too much about my signs. I don't really care that it's negative because I'm releasing or I'm gaining or whatever. It doesn't matter in terms of the grams. Okay. And it's a multiple choice question, so it doesn't really matter whether I'm showing my work is positive or negative. Okay. So, and then the molar mass, you would have to calculate that, but we get 32.0 grams of CH3OH per 1 mole of CH3OH. And that gives us the grams, and that's it, 3.2 grams. There we go. Number 22. Given the enthalpy change for the reaction below, and here we have the reaction, we have CH4. What is the name of CH4, the compound? CH4? Methane, remember? 1 carbon, the prefix is meth. If it's only carbon and hydrogen and only single bonds, that is what we call an alkane, which means the end of the name is ane. So we have methane. So we have CH4, and in order to break that into a single carbon and 4 hydrogens, we have to put in Z kilojoules of energy. So that's the energy it takes to break 4 bonds. And the question asks us, what is the energy to break 1 CH bond? So what would it be? It would be Z over 4. The energy required, what does it say? What is the average bond dissociation enthalpy? So it's either going to be, right now we know it has to be a quarter of this, yes? Okay. And then we have to think bond dissociation energy. So are we breaking or forming the bond if we are dissociating? Breaking. So that's going to be positive. Are you guys good there? Yeah? Okay. I didn't want to move on if you were still thinking. Yeah? Okay. All right. And last, oh no, not last. I think we got 34 as well. We have our coffee cup calorimeter. And if you've forgotten what a coffee cup calorimeter looks like, it looks like this. We generally use it in labs just because it's cheap and it's easy to make, and you can have one for every, group of 2 students or whatever. Is the insulation of a coffee cup perfect? Usually not, right? So in real life, you're not going to get perfect results with this. You can get professionally made calorimeters that insulate a lot better than these styrofoam cups. You guys probably don't even know what coffee cups are anymore because they don't make them out of styrofoam because it's bad for the environment, right? You just think paper cups, but they used to be made of like styrofoam, like the packing material, right? And so they were quite made of foam, insulated, okay? So we have this experiment, and it says we mix two solutions together. So we had solution A, and we had solution B. Which of the following assumptions is commonly made? So this is something we would do if we were actually doing a lab in order to make it so that we can just do the calculations easily, okay? Would we assume that the heat capacities of the solutions are equal to the specific heat capacity, specific heat capacity of the solutions are the same as the specific heat capacity of water? Yes.
If it's true, because the concentration is too low, right?
Yeah, usually we're just like, it's pretty low. Now, is it actually true that it is exactly the same? No, it's not, but we do make that assumption because usually the concentrations are quite low, okay? The reason that we don't get specific with it is you would have to go and get a table of each concentration of each solute. Can you imagine doing that? Every solute, every concentration, you'd have to look up a different value. That's crazy. So we just go, close enough. Water's pretty good. It's mostly water anyway. The amount of solute is small compared with it. So this one is true. Yes, did we assume this? Do we assume that the calorimeter is insulated sufficiently that we can ignore the heat loss? Does that sound like something reasonable to do to make your calculating easier? Yes. Okay. Is it going to be perfect? No, but we're going to make that assumption because it makes our calculations easier. Do we always make the assumption that the chemical reaction will be exothermic? No, because that, you wouldn't have to do that. Maybe the solution gets colder. And you're like, wow, that was endothermic, dang. And I assumed it was exothermic. Sucks to be me, So that one is a no. So your answers are 1 and 2 only. Yes? If you're mixing two solutions, you may get a precipitate or you may not. Yeah, it just depends on what you're mixing, because you could have a reaction where it's not just a formation of a precipitate. You could have other things that are reacting in different ways. Yeah. Sometimes actually what you'll do is you'll be using this to, if you weren't just mixing two solutions, you could have just something dissolving. So you could add like a solid in there and stir it, right? And you could see sometimes when you dissolve things, that's exothermic. Sometimes when you dissolve things, it's endothermic. So yeah, we don't make that assumption. Yeah? Okay, cool. Last but not least, if it is known that the specific heat capacity of water and the specific heat capacity of iron, so we know water and we know iron, which of the following statements is true and is a direct consequence of the difference in values? Water is a poorer conductor of electricity than iron. Well, that's just stupid. That has nothing to do with heat capacity. I mean, they both have to do with the fact that they have metallic bonding. Yes. Heat conduction and electricity conduction tend to go hand in hand, but they're not actually related in any particular way. So no. Iron has a higher density than water and will thus sink when placed into a beaker of water. What does that have to do with heat capacity? Absolutely nothing. Ooh, pen battery low. Let's pop you back. Adding equal amounts of energy to equal masses of water and iron will cause a greater temperature rise in the water. So what the question is saying is that the specific heat capacity of water is greater than the specific heat capacity of iron. If heat capacity is high, Will change in temperature be higher or lower? So given the same heat applied to the system, if the specific heat is high, will delta T be greater or lesser? It'll be lesser, okay? I should have said greater or smaller, but I don't know why I said lesser. I'm gonna put smaller. Weird word choice, but anyway, it doesn't matter. Yeah, because if you got Q equals MC delta T, if the heat is remaining the same, if C is bigger, then delta T has to be smaller in order for Q to remain the same, okay? And we're told that the masses are equal, so we can just ignore the mass term, okay? So is it true that equal masses of water and iron, you'll get a greater temperature rise in the water? No, because water has a greater heat capacity. It will have a smaller rise in temperature. So that's false. Adding equal amounts of energy to equal masses of water and iron will cause a greater temperature rise in the iron. Well, it had to kind of be either C or D, didn't it? Right? If C is false, then D must be true, right? I suppose E is a possibility, but it seems highly unlikely. Adding equal amounts of energy to equal masses of water and iron will cause the same temperature change. That would mean their specific heats would have to be the same, which is not true. So answer is D, and that is it for that. How are we feeling about thermochem? I know you did it all by yourselves over the phone. Let's get a thumbs up, thumbs down, thumbs in between. Okay. Yeah. So I've got nobody going like, oh my God, I have no idea. So okay. And we're going to go through the rest of them, so it's all good. Yes. Yes, I have to go and throw up all that stuff. So I will do that this weekend. Okay. Yeah. Could you do me a favor and send me an email saying, Miss Spence, please go and do this? Because that will help remind me. Any of you who want to do that, or you can message me on Teams or whatever, be like, Miss Spence, go and do this. Okay? Yeah. Thank you. I will also write myself a note, but you never know. I lose things. So. Make AP Classroom available. But I don't have all the questions up necessarily. AP questions available. Have you all signed up for AP Classroom? Yes? If you wish to take the exam, you need to sign up for AP Classroom. Is good? Okay. Speaking of the exam, at some point in the not too distant future, you will need to decide whether you are taking the AP exam or not. Okay? So if you did not take 11 enriched last year and you have not done self-study on it, you might think, do I really want to do all that self-study between now and May? I'm not sure. And that would be a choice that you would have to make. If you are just taking this course for the experience so that you want to go to university, but you don't want the stress of writing an exam, that's also perfectly fine. You don't have to take the exam. If you feel like you've got 5 AP courses and that's just too many exams all at once and you just want the experience of getting some test writing, but you feel like maybe 2 exams or 3 exams is enough, that's also fine, okay? So whether you choose to take it or not, totally up to you. But when they give us a deadline, that's like a drop dead deadline. You don't sign up by that point, you don't get to write the exam. Okay, so I don't know when that is yet. We'll get news. Ms. Riley will send out information and she'll make sure that you guys get the information. You'll get emails about it and all sorts of things. Yes? She's in charge of all the AP stuff. She's the AP coordinator for the school. Yeah. Okay. So, yeah, when I know more, you'll know more. In fact, you might know before me. Yes? You will be paying school cash online. It'll come up. Okay. Oh, and while we're on that topic, school cash online, I think it opened up yesterday for your workbooks. So these are the lovely workbooks that you get. They aren't free. Sadly, they do them for cost. They print them for cost at the school district. But you do have to pay for them. So if you could please get your parents to go to School Cash Online and pay for the workbooks, I would much appreciate that. Otherwise, I'll have to track you down later on, and I don't want to do that. So now, the other thing is, though, that if it is a financial hardship for your family, go talk to your counselor and they will have the fee waived, okay? Because we don't want anyone to be like, I cannot afford these books and that sucks and life is just terrible. Okay, we don't want anything like that. Also, if you are an international student, I believe your workbook fees are waived. If either of those two are the case, also, if you could just let me know, because that way when I get the list of people who've paid and who haven't paid, I won't come after you and be like, oh, you haven't paid yet. Come on, let's get the money. Is good? Okay, excellent. Let us go then to, how did the interactive activity go? Your little spectrophotometer? Was okay? Was it worthwhile doing?
A little hard. Yeah.
It didn't work on a phone. Yeah. Sorry about that. Okay, so maybe next year I have to say, do this on a computer. Didn't work on your laptop? Oh, that sucks.
Yeah, it was kind of hard to read.
Okay. Yeah. Do you guys all feel like between the videos and everything, you kind of got the gist of it, though? Are we okay?
The video helped.
Anyone not good? What video? There's videos at the end that you can watch if you didn't get the activity or whatever, and it walks you through the whole process. So you watch somebody doing it rather than doing it yourself. Okay? Yeah. All righty. So we were on 1.7D last day. We got to here-ish. And we were busy watching this little video here. And by the way, if you got confused at all yesterday by the whole part 1 of the experiment, part 2 of the experiment, blah, 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 I did a much better job teaching that in block 8. So if you're like, I'll just check that out over the weekend, feel free, okay? And the videos, both videos are up, your block and the other block. How chemists use Beer-Lambert law. So basically, after part 1, do you guys remember what part 1 is? This is page 70. Do you remember what part 1 of any spectrophotometry experiment is? Calibration, yes, you have to zero it, okay? So number one, you have to zero it, zero and calibrate. Part two, yes. Oh yeah, you got to heat the light bulb up. I actually don't want all those things. I just kind of want like the broader strokes. So you zero and yes. Yeah, find the lambda max. Find the ideal wavelength.
That's using the line.
That one is, no, this would be, no, the blank is like zeroing and calibrating. Yeah? This is like what we were talking about yesterday, where you just take a certain concentration and you plot wavelength versus absorbance. Because quite frankly, on the AP exam, they're not going to ask you anything about zeroing it or anything like that, other than, oh, so-and-so forgot to zero the spectrophotometer. What would you expect to happen to your results? We'll talk about that in a little bit. Okay. But for now, we're going to just finish this up. So find lambda max, and then after that, this would be like a part 3. So if you remember last day, we had stuck, or this guy had pretended to stick all of these cuvettes. These are called cuvettes. Into the spectrophotometer and gotten all these different absorbances and then plotted the absorbances, and they got a curve. Now, it's not a good idea with Beer's law to extrapolate past your data points, okay? Because what'll happen is that it's a straight line, but then it kind of goes a little funky at some point, yeah? So don't extrapolate. Or extrapolate as little as possible. But that doesn't mean that you cannot use your curve to find the concentration of an unknown solution, because if we have our unknown, here's our 0.47, and that is somewhere within our data, we go to 0.47, and we say, what is that concentration? And that is approximately 0.35. Okay, and that's where we got to last day. And then there is do the math. So you'll get the y equals mx plus b equation, and you will plug in the absorbance which is y of 0.47, and then you will solve for x, because x is the concentration, right? Because we've got the graph, which is absorbance versus concentration. Concentration is x, because it's on the x-axis. Absorbance is y, because it is on the y-axis. You solve for x, which is the concentration, and you get 0.34. Is good? What is the unit of absorbance? There is not one. Yeah. Yeah. Yes.
So the units for absorbance is a percentage, or
There's no unit for absorbance.
so it can go above 1?
No, it really can't go above 1. Because like if you, that would be like 100% transmittance. Yeah.
Oh, so still like the
Or actually, it would be 0% transmittance. So that would be like opaque.
Yeah.
Yeah. Yeah. No unit for absorbance. Yes. Oh, absorbance actually goes from 0 to 1. I know I was saying like 1,000 yesterday, but that was just because like I got excited. I don't know. Yeah, absorbance goes from 0 to 1.
So is it related to percent?
Yes. Yes. Well, I don't know. Let's not worry about it too much. Okay, I'll let your chemistry professors worry about that when you get to university. You're not going to get any weird data like that in the AP exam. Okay, and we got so much to cover this year that I'm not going to worry about things that go outside of the AP exam. Does that sound fair enough? Okay. If you want to talk about it at some other time, though, I'd be happy to like bash my brains against a wall with you. Okay, so we like drop by during flex or something like that, or before class or whatever, and we can take a look into that. All right, important considerations for Beer's law. Absorbance of unknown values must fall between the standards. So here's your standards. Those are the ones that you prepared, those little test tubes of known concentrations. Remember the word standard means a solution of known concentration. Okay, that's going to come in handy here. It's also going to come in handy in titrations because you need to have a standard to titrate your unknown against. So you had 5 standards in this spectrophotometry experiment. You know, if you go back and you look, you're like, these are our standard solutions. Okay. And we got 5 of them. And so on our graph, we have 1, 2, 3, 4, 5 dots. Unknown number 1 falls in between, or actually we've only got 4 dots in this particular case. We've got standard 1, standard 2, standard 3, standard 4. Unknown number 1 falls in between those. So you can do that. If you have unknown number 2 and it falls further than your standards, you need to add more standards to use your plot to predict that concentration. Does that make sense?
If it's unknown 2,
Yeah, unknown 2, you can't do it without more standards. Yeah? Or you can dilute the sample. So you can add more points to the line, more standards. Or you can dilute the sample, and the sample is the unknown, because right now its concentration is too high to fall between the known standards, yes? But you could dilute it. You could do a 1 in 2 dilution or something like that, make it half of its concentration, and then it will fall within, and then you would just have to double your concentration to find the original concentration. Does that make sense? Yeah? Okay, cool. In university labs, you'll be expected to find the equation of the line both by plotting and finding the slope and y-intercept of a hand-drawn graph, and by entering the data in a spreadsheet like Excel, making an XY scatter plot, and adding a trend line. I'm not going to teach you either of those things. I'm going to assume that you have learned this in physics or elsewhere. If you have not, here's how to graph things by hand. Here's how to graph in Excel. You can watch those if you want to, but we don't got no time for it. Okay. Okay, next page. Beer's law plot, absorbance versus concentration, is called a calibration curve. So this right here is a, ooh, that's a weird A. Why you not erase? Ugh. And you'll notice we call it a curve even though it's a straight line. That's okay. Now the slope is the molar absorptivity. It's that epsilon. Because if you remember, absorbance is equal to, what is it equal to? Epsilon times B, which is the path length, times the concentration. And B is going to be, this is the path length, and it is constant, so we can ignore it. And usually it's 1. Usually the path length is 1 centimeter. So really what we're looking at then is actually not that it's constant, we can ignore it, that it's 1, so we can ignore it. So therefore, we can just say A is equal to epsilon C, because this is 1. Yes?
So, one, like, the union also.
It is also constant, which is why we have a straight line.
Yeah, so.
Yeah, I should not have said that about the path length. It's because the path length is 1 that you can just toss it out in terms of figuring the slope.
Oh.
Right? Yeah. So for this graph, we have y equals mx. Does that make sense? Okay, cool. So if they're like, here's a calibration curve, please tell us the molar absorptivity, you can just figure out the slope of the graph, and Bob's your uncle. Is good? What time is class over at today? 11:35. Okay. Oh. Oh, that's because that was used to be Friday. Flex made the blocks like, but now they're different blocks. It's very confusing for me. I have to keep looking at my wall. I'm like, I don't know what's happening. Okay, this just explains that, and there we are done with that. And we are actually going to go to our other workbook now. We are going to go to page 11 in the green book. And what I would like you guys to do is I would like you to try, because you are all brilliant people, I don't think you need me to teach you how to do this first one. I think you could just do it on your own. Do you want to try it? Page 11 in the green book. And if you get stuck, wave me over. Also, if you get stuck, ask your partner. You okay now?
Tell me where this goes.
Right here.
I see that was like.
Yeah. Yeah, folks, you don't have to change from milliliters to liters because it doesn't specify. It just says volume. You can use milliliters.
I don't think that's right. Are you supposed to use there? Wait, never mind. It's per minute, right? So when you divide it by
When you get an answer, check with the third person next to you. See if you're getting the same thing.
oh yeah. Never mind, I didn't do that. So you would do like 4, 5. That's 1.45.
We just keep
You
going.
get that?
You can keep going after you're done, yeah.
Really sure?
Absolutely, yeah. No, yeah, you do it, yeah, you do that. Because you're like, what is happening? Yeah.
I got 185 Dorothy.
Yeah, if we ever come across something, if you weren't in 11 Enriched last year and you're like, what was up with that covalent bond graph, and you want to come in during Flex and have a chit chat about it, please, please do. That is exactly what Flex is for. Or if you just forgot it from last year.
It should be 0.11. What? Oh yeah, never mind. Yeah, 0.01. I read my calculator.
Wait.
Because she was telling me what to do, and that's what she Wait, Dorothy.
Hi. Yeah.
Example 2. Will you add all these and then
Did you guys, you're checking my work for me because you know how I always make mistakes. Did you guys get 4.12 milliliters per second for part A? Good. So I did not make mistakes. Now, one thing I do want you to do is I do want you to check that you showed all your work, including what you are solving for, including your units in your work. Because when you write the AP exam and when you write your tests for me, I will be looking for those things. The markers will be looking for those things.
Wait, do you use this or this? Wait, if we add all this one, I should one there.
Yes.
Or am I? Nope. Yeah, it was 0.06 or whatever. Right.
When you were doing part B, did you subtract the 2 masses of zinc? Did we do that? Because we started with some and then we finished with some, so that is the amount used. Excellent.
Right? This is on. Yes. Okay. And then for this one,
Wait, are the rates always?
Huh?
we use the liters, right?
Rates are not always
And then change the liters.
positive, but
Okay, wait. If it says balls, like.
But it's one of those things where it depends on how you say it. If you're like the rate of use of zinc per minute is positive, but if you say what is the change in, yeah.
Oh, I'm using this or this. Right? So don't you just add all this, then divide by that?
No.
Oh.
Don't we just add them all and divide by that? No. No. Shall we take a look at, do we feel good about this one? We would just change this to moles. Okay. And then we would get our answer, whatever the heck it is. Does anyone want to go through that one at all? No? Okay, cool. I did want to take a look at this one, and we're also going to talk about complete and net ionic equations while we are here. So if we have zinc and it reacts with hydrochloric acid, HCl, what state is zinc? Solid. And if we have an acid, what states are acids? Aqueous. What type of a reaction is this? Single replacement. So we will end up with Zn Cl2 because Zn is 2 plus and Cl is -1. And that's going to, what state would that be? Aqueous. And what's our other product? H2, and that is a gas. Now, if I said to write the complete ionic equation for this, would you know what to do? So our complete ionic equation, I'm going to just ignore the states here for now. Oops. What did I forget to do? I forgot to balance it. I need a 2 there. So I would need a 2 there and a 2 there. Did you remember to put your charges on your ions? Okay. Where? Here? What's the charge of zinc there? Never mind. Okay. Why do we have no charge on zinc where it's yellow? Because it's the solid, it is in its elemental state, it is neutral, 0 charge. Yeah. Do we have any spectator ions? Who's the spectator ion? The 2 chlorides are the spectator ions. So if you wanted to write the net ionic equation, what would you do? You would just get rid of them. Now, when you are asked to calculate the average rate of reaction, do not add them all up and divide by whatever. Okay, an average rate of reaction is equal to the change in quantity over the change in time. Did you guys do that in physics? Like when you were finding average velocity, you would find the distance at the start minus the distance at the end, or vice versa, sorry. You know, and then you would do it over delta t, delta d over delta t. Same thing, when we are finding an average rate, you're always going to do the change in the quantity over the change in the time. So do not add them all up and divide by 1, 2, 3, 4, 5, 6. Okay, don't do that. Just take your initial minus your, or sorry, your final minus your initial. Final mass minus the initial mass over the final time minus the initial time. And I don't know what that equals. Yeah. Huh? Yeah, you can just write, like, so for what you would need to write, you could say rate equals delta m over delta t, and then you would show your work. Yeah. So you don't have to write all of this, is unnecessary. This is just unnecessary. Write this. Okay, so that saves you a lot of writing. Is good? Okay. Yes. Oh, it should be 0. What is wrong with me? Thank you. Yeah, that should not be 4 seconds. That should be 0 seconds. Thank you. Oops. Do we feel good about that? Okay, so there are more questions on this stuff. It does include some equations, so I'm going to get you guys to do pages 14 to 16 in the green book. And I would like you to do pages 74 and 75 in the blue book. I don't know. Didn't we already do 13? Oh, you guys could also do page 13. Oh, sorry. Yeah, do page 13. Sorry, 13 to 16. Because that'll do a little tiny review of complete ionic and net ionic. Yeah. If you're feeling dodgy on complete and net ionic, we will go over it more next day if you would like. Okay?
Oh, really? A what? Really? Bodies are a reaction. That's what we call them. Because I'm not meeting. We're music. It's not art sales. I know. I suck at drawing. By the way, FYI. No, you're not. You're not. But you don't have meetings today, Okay.
Bye. Have a good weekend.
Is there like any practice quiz on the different
Practice quizzes on what?
on like the
What unit?
like the unit we're doing for
Oh, the unit we're doing right now?
is there like a test? So
Yes. We've hardly started it though.
I'm in. Is there one? Huh?
Well, to be honest with you, right now, say for example, the 1.7E,
Yeah.
that's an AP question right there.
Oh, okay.
So that's your practice quiz.
Oh. Wait.
You're like, oh, I want a multiple choice?
Oh, are we allowed to give requizzes? We have no requizzes, right?
No requizzes, no.
No requiz, no retest, no omissions, like
Just you get what you get.
okay.
I'm gonna get destroyed.
Same.
No, you're gonna be fine, bro.
But yeah, this is literally a question from an AP exam.
Oh.
Oh,
Oh.
Yeah?
Okay.
And it does, yes, they do have like parts A through F. So They're kind of crazy.
Alright, this weekend. Finishing the entirety of.
And if you're like, oh, I want more practice, guess what? I only assigned one of them, but you can just keep going.
Oh, there's a lot.
Oh yeah.
Is there like an answer key to it? Or?
Oh, you didn't
like
get the
a-
answer key?
There is an answer key right there. Oh, wait. Oh,
The
yeah.
answer key,
yeah,
answer
I
key.
have it.
Yeah, you're good?
Yeah.
Okay.
Thank you.
This part, right?
Huh?
We didn't learn this yet.
We've not done that yet. No, we're gonna do that after we've done the reaction rates.
Finish this.
Yeah.
And
I should probably like switch
This
these,
one.
but whatever. I
this
don't-
and this.
I'm Spec.
Bye. Once we're finished 1.2, there's gonna be a quiz.
So,
There will be no quiz on spectrophotometry because I don't quiz on AP stuff.
huh?
There will be no quiz on spectrophotometry because I don't quiz on AP stuff.
There will be a test.
Not on spectrophotometry because it's AP stuff.
What? That's crazy. Okay. Thank you.
Okay, so like if you're, I know you were saying like over the summer you're feeling like a little dodgy, overwhelmed, whatever. More than that. Yeah, so you can choose to just focus on the regular 12 stuff. And you can do like, you can look at it every once in a while or whatever, but like your mental health is more. Yeah, yeah. Are you seeing someone? What?
I mean, I'm reaching out to friends and stuff. But
Yeah,
then it's very messy.
yeah.
Is it so visible on my face?
But these colors are shady.
You're like, I'm not trying to off myself by scraping my chin. Okay.
I
know- I
know
Good,
it'd
good.
be better off here or here.
Okay.
I did mess up all of my guys, so I was supposed to finish it this week. I could have been finishing it by.
Like, honestly, like, if you just say to yourself, I'm just going to focus, I'm going to pretend that I'm taking Chem 12 rather than Chem 12 AP. I'm just doing all that extra stuff. I mean, you can do it when we're doing stuff in class, but don't worry about studying it.
Oh, I have time. I could really.
Well-
I did not expect to be so hard. Especially with the bond filters and stuff, we actually never all stuff.
Yeah. So, like I said, we don't need to know any of that. Regular Chem 12 stuff. Yeah. So just.
In fact, I'm kind of happy and finding a big challenge because I don't want to sleep through all my classes.
Okay. Okay. Yeah.
Especially the first class, I would basically send them to a
Yeah. Oh, okay.
So for that seeing people, I might go see my counselor.
I think that would be a good idea.
But they're extremely busy.
They are extremely busy right now, but, and they said they wouldn't have their doors like locked until
They're
Friday.
locked.
They're locked until Friday, but on Monday, they'll be open again because there's no more first changes after. Like, and even those ones are just like,
Oh, for second semester, do we did the course change right now?
you could if you wanted to, yeah, yeah. But I would say wait till after Friday because they're dealing with all the semester one stuff right now.
Oh, so the course change is right now over the semester.
Unless you
That's
have
why
like,
she was-
unless you have like a double switch, like something from semester one had to change to semester two to make the semester one change work. Do you know what I mean?
Yeah.
So, yeah, that kind of thing. But I think after today, and they did say also that if a student needs to see them for like a reason other than I don't like my teacher, I would like a different course, please. That they are available and all you would need to do is just go
I like
talk
how-
to the office and they'll get you into there so you don't have to like, you know.
Especially glad that I got this class with you.
Yeah,
Because and then
I do.
Mr. Wagner, that would be good stuff.
You know what? He's actually a really, really, but he comes across as very,
Still.
yes, but then if you actually like get to know him, he is like super compassionate.
Yeah, that's what I heard.
Yeah.
The hard part is good. Are you gonna take a break?
Yeah, I am.
Yeah.
But, you know. Are you gonna take
speak of it.
You got personal drama?
A lot of it actually.
No.
Which is why I wrote this coach.
Oh no. Just toss that nonsense to the
Yeah.
side.
Oh, I'm not gonna let it affect my ears.
Well, don't let it affect your brain either. Like, just.
That's the hard part.
Yeah.
It's relation to the
It is really difficult. I do understand that because I also like thinking.
I love all kinds of conditions. My mom said I had mental health problems.
Yeah, definitely. Getting to see a school counselor, they might refer you to someone as well, like it can be more than what they have time for. Yeah. I hear you, but it can be worth it.
Because I generally don't have the time. Like even now, a lot of stuff I do because I've only been here for a year, but I have 135 hours. I have a lot of stuff, so I hope to do that. That's fun.
Oh, that goes. Nothing, everything else falls apart.
That's what people have been telling me.
Right?
And it's already-
So sometimes you have to say, okay, I am dealing with my mental health. I've been very lucky in that I have my summer every year to deal with my mental health. Right?
You look
Because I'm
better.
mom.
No, every time.
But-
For me,
yeah.
every summer is just same thing. It's like by the end of it, I get high functioning depression, and that's it.
But keep checking in with me, okay?
I will.
Yeah, thanks. I want you to. I really want to know.
Thank you so much for again.
Yeah,
You've been helping out a lot.
good. Yeah, and like I said, if there's anything I can do for you, other than be like, go see your counselor, let me know.
No, I will come to you for help. Again, I want to ask my stupid doubts, but then I'm like, it's just going to ruin the class at this point. No, I'm going to, come on, I'm not going to keep asking you the page every 5 minutes.
Okay, the page. You know what? Jofi can tell you the page, right?
Yeah, that's what I'm doing.
Yeah, that's true. That is true.
Because I'm spacing out every 5 minutes.
Yeah.
All right, Miss Let's take care.
All right. Have a good lunch. Have a good rest of your day.